Yep, I got the recording started there, Karen. I just will have to check and see if I'm allowed to share it post meeting. See what are corporate policies. All right. Can we see the main screen there, Emmanuel?
Yes.
All righty, thank you. It's coming in.
Well, we do it as a percentage, so, but the enough. Yeah, so it's, that's why I'm playing for this. I forgot that I did that last time.
Okay, anybody with questions can put them into chat. Towards the end, we expect to have time to take questions. Everybody's coming in on mute, which is great. Okay, we're just going to jump into it right off the bat. Can you hear me well over the mic, Emmanuel?
Yes, I can, Joy.
Okay, good. I was worried it was too noisy. Alrighty, so EMT modeling and testing session. Nova Scotia Power, some years back, were required to meet certain renewable energy standards. Starting back, we can see 2015, our 25% requirement. Just kind of giving some background to how we got to where we can be offering this this presentation. And then it jumped up to 40% starting in 2020. And now we have to get to 2030 with 80% renewable energy. Nova Scotia is fairly remotely connected to the rest of the Eastern Interconnection. And we do not have a lot of hydro. We don't have nuclear. We have wind. We have a lot of wind. Wind is a high IBR resource. So in order to get to 80% renewables, we need to be able to allow for some hours where we're running with 100% IBR. So we just take a look at the existing system in Nova Scotia. In Nova Scotia wind, right now we can be getting close to 100% IBR at light load. We have wind, and we do curtail for stability at some points right now because older wind farms are not as robust and do not ride through as well as some of the more current plants that we're seeing coming through. The wind is much more robust, supports their point of interconnection much better. So we curtail some of our legacy wind farms for stability when we're running very high wind. We have an SBC, which we do consider when we're looking at IBR as an IBR impacted by low short circuit MVA and other conditions that impact IBR. We have an HVDC between the island of Nova Scotia and the island of Newfoundland, Cape Breton Island. Nova Scotia is a province, Cape Breton is an island, and the island of Newfoundland. And that we also consider as an IBR when we're setting guidelines, and it provides very good voltage and frequency support between Nova Scotia and Newfoundland. We have very limited tie lines to neighboring areas. We have import limitations, fairly restrictive ones from both New Brunswick and Newfoundland, the two adjacent provinces. And there's a high impact for single contingency. If we're running high imports, we can have a significant impact for loss of a tie line. A loss of tie line with New Brunswick under high import creates an island for Nova Scotia electrically, which gets into under frequency load shedding and creates conditions that are very difficult for inverter-based resources to stay online. And also, if we lose the imports from Newfoundland, that can be up to 475 megawatts landed in Nova Scotia, and that is a significant impact. For those of you on the call who have larger systems, when I talk with Nova Scotia, it's about a 5,500 megawatt peak load. Maritimes area is about 5,500 megawatts peak load. The Nova Scotia part is about 2,400. So just scale it up. If your area is, a 30,000 megawatt system, then just think of multiplying everything I say by a factor of 10. So large scale integration of IBR. We have this system, which was traditional system. We started putting on wind because really that's what is available in Nova Scotia. And we reached limits about a decade ago. It was like, look, with the technology at the time, with the wind technology at the time, we could not increase IBR without getting to unacceptable levels of instability for certain contingencies. We were hitting where we were having to curtail wind. We did at that point, about 8-9 years ago, understand that additional synchronous inertia would allow more wind to be connected. So we did add a fairly large requirement for synchronous inertia to any wind facility coming online. They had to put synchronous support or equivalent at 3 megawatts seconds for each 100 per each installed megawatt. So it got to be a fairly large requirement. And this was to provide for ride-through capability. We're finding that legacy wind trips very easily for system disturbances. And also damping. We find that post-fault recovery in legacy machines is poor. And even with more modern machines, we find that we do need additional support at the point of interconnection for wind facilities and really for grid following facilities to be able to ride through and to continue delivering active and reactive power during disturbances. We do know that for large-scale integration of IBR, we need to have power electronic controls, tuning, and damping. For that, we need to get into EMT study. Frequency support can be covered mostly in PSSE, and PSSE is our software that we use for RMS studies. If you use a different software, and there are many out there, then that would be the same impact. And when we say PSCAD, it could also be another software for doing EMT studies, such as EMTP. So controls, damping, and tuning, we need it to go to EMT software. PSCAD we use in Nova Scotia to look at active power contribution post-fault. What did damping look like? We needed to get into EMT studies, reactive power control strategies for the system as a whole. Fault current contribution is not so much related to our EMT studies, but we did have independent consultants come in. They did a review of our PNC practices, our PSSE, PSCAD, and Aspen models, and how we would be modeling IBR going forward. So, large-scale integration of IBR. We had this target put in front of us, 80% renewable energy, which translate into 100% IBR in some areas. So we developed a plan in about Q1 of 2022. We developed a study scope on how we would get there. We engaged consultants to support the model build, to get the EMT model built in PSCAD, and to provide subject matter expert as they had global experience. And also then to build a team expertise in-house at Nova Scotia Power in EMT studies. So we built the system model in PSCAD, benchmarked against PSSE late 2022 and into 23. And then at the same time, we started to have a lot of the interconnection requests come in for new wind battery facilities as the next wave of renewable targets were coming into effect in 2030. The plants need to start going online now. So we were starting to get mandates to bring in certain amounts of wind batteries. And we needed these facilities to come in for system impact studies. And as we were learning more about EMT studies, the first thing we found was like, oh, these models are not great. We need to start testing them before we start putting them into our case. So that was about 2023. We started getting into MQT for our EMT, our PSCAD models. Initially, it was by a consultant, with them training us, with us reviewing results, but now it's internal to NSPI that we do model quality testing in-house. Validation against field data for one project back in 2022. We also had data from the field for disturbances, and we recreate in PSSE and PSCAD and benchmark against each other. And that's an important step to get to running large-scale studies, as you must validate your results from field to your PSSE to your PSCAD. So large-scale integration of wind, 2022. This is still ongoing in Nova Scotia. We did put out stage 1 report in fall of 2023, and we're hoping to get a stage 2 report out this year with more EMT study findings in that report, as well as our PNC review and other learnings that we have based on the studies. So large scale integration, get a plan, build a model. We found that we had to test a model, and then you have to validate your models, your system models against reality. It's no good to get PSCAD models or EMT models and run studies if you don't know that they are accurate. Is this real? So to compare to your system, when we look at Nova Scotia, we're connected to New Brunswick, and PEI is connected very closely by New Brunswick, and then we have an HVDC system going to link going to Newfoundland. So in our largest area model, which is the maritime area, which covers Nova Scotia, New Brunswick, and PEI, is about 1,100 buses. If you're trying to get a comparison for the scope of work that we undertook and what you would expect for your system. So about 1,100 buses in PSSE. So we decided what network we wanted to bring into study. And this was in consultation, of course, with an expert in EMT studies. And we said, okay, this is where we're going to put the boundaries. We're going to cut it off at this HVDC link in New Brunswick, and we're going to cut it off here. We're going to make it into a nice PSSE package. And you take, with that size of a system, it needed to be broken into sub areas for study, so that when you're running it in simulation, you can run on different cores. So we have 12 sub areas. Nova Scotia is divided into 6 sections. New Brunswick is divided into 5, and then PEI, a much smaller province, is in its own sub area. And then when you develop this model, you need a separate page, separate project page for all of your IBR, so that when you're running them on your high-powered machine, you can run multiple cores, and it speeds up the simulation runs. We would recommend that the maximum effort go into your PSSE case before conversion. The better you have your PSSE before you start the conversion, the better the more usable your product will be at the end, because you're going to be developing your team of experts for EMT if you don't already have it. And they're used to working with whatever your software is for your RMS studies, us as PSSE, or like Power Factory, whatever you're using. Make it as close to your PSSE from a layout, from your one lines in PSCAD. Keep it looking like what your folks are used to seeing, because they're going to need to get up to speed fast. The closer you are to what you're used to seeing, the easier this will be. Time permitting, I do have a couple of backup slides, and we can take a look at that. If anybody has interest, you can just make a note and ask me at the end, and I can take a look at it. The Nova Scotia Power part of this is about 500 buses, and that's where we have very detailed for these studies that we're doing in Nova Scotia. So user-defined models where possible. Otherwise, we tune generic models. And then in the adjacent area outside the Nova Scotia area, we use generic models, basically imported from the PSSE. And we don't really worry about those too much unless they cause a problem or they're have some instability in the run. We'll go and we'll take a look at them and tune them further there. But our focus is on this footprint for Nova Scotia. Unless there's something close to a tie line or close to a border, like there was a wind farm just over the border. It wasn't in our real area, but we had to go look at it a little bit more closely because it was impacting a facility on our side of that line. So for entities that have large systems or very small systems, you decide where you want to put heavy concentration on effort to get the models in. So the tuning of these existing models, that was challenging for our thermals, our existing thermal machines. Would take like our mod standards for folks in North America. We have mod standards that require testing of our thermal units, and we get a report back from our consultants, and they'll give us the block diagrams and the tuning parameters, the type of models. So we referred back to those a lot of time, a lot of going back and forth to get those models tuned. Like I say, this would be a PSCAD here. This would be like part of a module in Nova Scotia, at a page for Nova Scotia. And these represent how you link those different project cases, like how I would link the northern, which we're seeing here, to, there's one in New Brunswick, central or south. And these are how you link those cases in PSCAD. If you're a PSSE user, you will notice in North America, you will notice these bus numbers. We import the bus numbers from our PSSE into the PSCAD. It makes it more intuitive for our existing transmission planning team to pick up the PSCAD and learn it without spending too much time on was the admin side, figuring out the nomenclature and things like that. So we tried to make it as intuitive as possible for people coming into EMT study from our traditional load flow and RMS study. So large area system study. What we do is, as we've been learning over the last couple of years, as we've been bringing on new staff, this year we bring on a couple, this year we bring on a couple, is when somebody learns something, we ask that they write up a quick tool on how to do stuff. So, because whoever is the last person in, the one who came just before them gets to train. So this one trains somebody, the next person comes, they train. So what we have now is a lot of tools here and these are short documents, but they are really invaluable if you're taking somebody who's learning without having to spend huge amounts of time with training. It's like, okay, get your PSCAD installed, go look on their website, do a few tutorials, then we'll talk on how to get you rolling. So to do a large area study, this is the tutorial documents put together. So Linda here, what do you do when you get a new PSCAD mod? So she had a new study. An interconnection request for a wind farm. So first thing you do is you redispatch your PSSE to PSCAD. You have your PSSE case, so your RMS case, the case that you created your PSCAD case from. You make the changes in your PSSE case, your RMS case, and then you import those changes into your PSCAD. So if I've got a load at 40%, I want to put the system load to 60%, I make the changes in the PSSE, then I redispatch it. We have a script, a Python script, and then we'd have a quick instruction to the users, just follow these steps. Here's the script. And, they will run into problems. That is just a reality of this kind of work. It is challenging. It is a lot of, it's a steep learning curve, but it's pretty manageable. We have a team of people here, some of whom were hired last summer, who can run model qualities bang, 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 and they are now running through system impact studies fairly quickly. Some had experience in power systems, some were straight out of university with power system courses, but really not familiar with this, so this is manageable. So you redispatch your case, you run your contingency analyzer, so you run all your contingencies you want to check. I got a few snapshots of those on the next page we'll take a look at. Creating reports, again, scripts. Reports can be popped out based on what you want to see. And there's a few more pages in this, learning notebook on PSCAD, but step by step takes you through it. I was saying, if you want to look at how you're going to do reports, this is what we call a frames folder. Frames, basically, if you're familiar with PSSE, this is like your channel file. It says, okay, for this project, IR's interconnection request, somebody created a frame to print out traces relevant to that farm, or we might want to look at all the generation in the east. So you just pick which frames you want to print as your case is running, as your simulation is running, what do you want to print? We're looking at contingencies. I know I'm jumping very quickly here. People can start asking questions. We're not doing too bad for time right now. I talk very fast. This is contingencies. We create contingencies to run in Excel. And again, we try and make them very intuitive. We're running a breaker backup here at a certain bus for a breaker, the east of the province. So we're saying there's a line of ground fault on a certain, the Lingan, so at a certain location on the line, at the end of this line, it clears another line and the breaker in 16 cycles. So this here, enable, disable. If you want this contingency to run for your particular study, you just put a 1 in here. Otherwise, you leave it a 0. And then this is the information pulled out by the scripts running to run your contingency. So again, easy to read once you know something about power systems, easy to keep track of. Running the contingency analyzer, again, whoever was into it the first couple, they got to do quick PowerPoints on what you do. These are only 10 or 12 slides each. It tells you how to set up your report files, how to run your contingencies. So this gets to be a very interesting one, and we're going to talk a little bit about model requirements and model testing, which is one of the primary reasons we're running this presentation for folks. Is we're now seeing a lot of need to run model quality testing. But what is a model? What is the PSCAD model? We're talking about one of the customers, and you were saying, like, look, they're trying to get their interconnection agreement signed. They say, well, look, it's just a model. It's not going to impact how the plant runs. But just keep going. It's like, whoa, hang on. PSCAD model is everything about how your plant is going to perform and how your plant is going to be able to interconnect. When they design control systems for IBR in particular, it might be designed in PSCAD a lot of times, or some other EMT software, could be in Hydra. But the code that they're going to upload into the control systems on site is pretty well identical to what's in the PSCAD model. So when we are running a simulation, if we have our Nova Scotia system well modeled, and we put this wind farm model in there and run, the results that we come out of that, we expect them to look very close to what you would see for the same event in real time on the actual system. So the PSCAD model, really what we're talking about here, when we say model requirements, that's about what we need to be able to model your system. But when we get into model test, it's not really the model we're testing. We are testing your control system. So with that in mind, Nova Scotia Power, we have model requirements. They are coordinated now across Atlantic Canada. The 4 provinces are fairly aligned on what we require. We have meetings. We have a transmission planning committee for this area. And we've kind of set general guidelines on what we expect to see provided by customers, generator owners, and this also would apply to loads where applicable, batteries, what we want to see delivered with your model package. PSSE requirements, PSCAD requirements, harmonics, documentation, and also model testing and benchmarking. We will be benchmarking them against the PSSE to PSCAD as well. And we will be testing fairly rigorously. And the other big one is in commissionings, we will do it again. In commissioning, we're going to look at how your system performs in tests. And we expect that if we run a test for a voltage drop in commissioning, the results should be looking pretty well exactly like what we see in PSCAD. If not, either your model is off or something is wrong. So it has to be resolved in commissioning. We are also going to be putting fault on the system. Line to ground, 3-phase to ground, or line to line was probably not advisable because you would see that, customers would see that, but we are going to be putting a line to ground fault either in the substation or on a line close to the point of interconnection and see if these new facilities are performing as they say they are going to do so. So model testing, like I says, not really model testing. This is control system testing. We validate the performance of a facility before it is deployed in the field. The plan is to demonstrate compliance with all requirements to connect to the NSPI grid. This evaluation is done in small models, single machine infinite bus version of the electrical network to verify its dynamic performance and stability. So it's a small test case. And this is another important one, which is going to align with the NERC alert, is models are required to meet a minimum level of performance prior to the SIS. We do not start an SIS for your project until the model has a certain level of quality, and other projects will jump ahead of you if they are ready and you are not. So the tests again, they're a collection of tests designed to ensure that plant models conform to the performance requirements. This is another document. Feel free to take a look at it, copy it into your corporate logo if you want, and use it and then revise it as you move forward and you learn more about what you may need for your system. If you haven't started this type of test yet, have at anything we got, we're quite willing to share it. So this is a sample of one of the sections. It is extensive, but it does not cover all conditions. There's there's a limit on how much we can test right now as we're learning and expanding our team. So when we started, we had a small set of 20. The number of tests we are running is evolving. I'm not sure. Manuel, what number are we up to right now? How many tests are we running right now? Do you know off the top of your head?
Like 347 last I
Yeah.
checked.
Yeah, that's a big number. When you're starting to hit 300, we'll talk a little bit more about that shortly. But you also have to decide what's appropriate. When we first started a year ago, we had 20 or 30. And that just the results from that and working through the issues discovered with a small subset of tests was as much as we could do. But now we're getting to more what we think is a fairly rigorous assessment. Boundary conditions are used to test a range of expected operating conditions, but also into criteria. So we cover, in that Smith case, we cover a range of conditions. So how did we get to having a test module? We reviewed test models and learning from other entities. So like ERCOT has a test module online. ATC has one online. AMO is the one that we particularly like because they use the same consultant as we do and the same software. So AMO has a test module online that we kind of said this works. So the basic scripting you can see here is an acknowledgement that it is coming from some of the core stuff is from AMO, but it's been modified and added to other scripting that works for Nova Scotia Power's specific system. Ours is more aligned with NPCC and NERC criteria. So to perform, this is a grid representation of the case, Thevenin equivalent representation of the network as seen from the plant's POI. Various resistors and inductors are included in the SMID model to accurately represent a range of grid conditions as seen from the POI. So the test module, we look at a range of scenarios, three-phase, two-phase, single-phase to ground, line to line, range of residual voltage. So is it a close-in fault and the voltage is down to 20%? Is it a shallow fault and it's only dropping down to 80%? So we look at some scenarios there. We look at different combinations of SCR and X over R values, and we test all control modes. Now, the MQT does have some limitations. We still need to go to the SIS to assess performance when connected to the grid, looking at control interactions with other plants, and to fully test fault ride-through and post-fault recovery. But the test module for the controls PSCAD model is picking up quite a few issues, and we are working through those with the OEMs, and we're really getting much improved models coming through. So Emmanuel, did you just want to just do a quick share of what the PSCAD module actually looks like?
Sure, Joy. Okay, let me just share my screen. Okay, can everyone see my screen?
Not yet.
Not
So
yet.
anybody seeing Emmanuel's screen?
Yes, we're
Yeah,
able to
we
see.
see.
Okay, go for it.
Okay,
It's just me.
perfect. Okay, so this right here, I have a generic wind farm, which I'm going to apply some of the MQT tests to. At this side, where the reference step component is, this is the actual SMIB model. So if I double click on this, I'll go into the component and it shows the grid representation as Joy mentioned earlier. So what I'll do now to run the test is to right click on this module, edit parameters. Before you run the test, you have to fill in these like relevant information, but I've already done that. So I'll just go ahead and pick the test I want to run. So right now I want to run test 17.01 to apply a three-phase to ground fault at the plant. So I'll select that, I'll click run. And then whilst the simulation is running, I can double click on this NSPI meter to get live results. So I could see the active power, reactive power, and the voltage at the POI. Okay, so whilst that is going, I'll just quickly mention the script we have here. Joy also alluded to that. So we have a script that allows us to run multiple tests at a time in parallel. So the number of tests you can run in parallel is limited by your PSCAD license. So right now on my machine, the PSCAD license I have allows me to run a maximum of 8 parallel simulations. But on our bigger machines, we can run 64 simulations at a time. So depending on how complex the model is and the solution time step of the PSCAD file, you could either get results every 5 minutes or the longest I've seen is 20 minutes. Yes. So as you can see here, if I go back to PSCAD, you can see that the simulation is running, and around 10 seconds, you should see a fault applied to the POI. So we're just waiting for the fault to be applied. Okay, perfect. So as we can see, a 3-phase to ground fault was applied at 10 seconds, and there is some residual voltage left here. Okay, so I'll just also quickly show some of the results we have from running like the full MQT on other like wind farm models. So we're able to take the results from running the simulation, use another script to generate this report. So based on the test, we have different graphs neatly plotted to show the results of the tests. Yes, I think that's the end of my presentation.
Can you hear me, Emmanuel?
Yes.
Okay, my screen just crashed. Just give me a minute. I've got to try and get it back. Can you share the presentation? Do you happen to have it handy?
Yes.
Because I've got to restart my computer here.
Okay.
Just give me a second, folks. This happens distressingly.
Emmanuel, you also have a couple questions in the chat, and you've got someone with their hand up if you want to address that while you're getting ready for Joy.
Okay. I'm sure we will take questions at the end of the presentation, but if Joy still
Perfect.
needs time, then yeah.
Can you hear me now? Okay, I'm on my phone. While I'm waiting to restart, if you can get the next screen, I can speak. I can see it on my phone if you want to bring up the next slide, and I'll keep going on that until I can get my computer back up. So what were we up to? Oh, I need younger eyes. Okay, where was I? Okay, EMT model evaluation and system studies. So the big thing we can say about it, it works. It works very well. When we first started, the best we could do was, okay, we can get the system up, we can run limited contingencies, limited scenarios. Like we couldn't run like 5 scenarios in PSCAD just because the amount of work it would take us to redispatch, the resourcing we had was limited. But now, 2 years after we started, we're in very good state for being able to run full cases. 1 second. I have to get my machine logged in, and nowadays I need 6 different passwords to turn on a computer. If it hasn't come to your utility yet, it's coming soon. Wait for it. IT is taking over. Let's see if I can get myself up here. 1 second. All right, well, that's going on. So the biggest hurdle we had was Poor performing plants. We had a lot of this when we first started. But the thing is, if we wouldn't have done all the work we've done on getting these models and getting the model qualities and working with the vendors, we'd be putting those poor performing plants in service. There we go, almost on. Add this device. All right, Emmanuel, can you hear me over this speaker?
Yes.
Back live, Unreal, fine. All right, we'll leave you with bringing up the presentation rather than moving me to wait, too much confusion. So where was I? Poor performing plants. That was the biggest hurdle. It took a long time to get a lot of the plants performing in our new studies. But that meant that we were finding problems and resolving issues. So while it was the hardest part of the last couple of years, it means that we are putting plants into service, planning to start, but they're in construction right now in a much better state than we would have than if we hadn't have gone through this process. Lack of EMT and PSSE dynamics trained engineers, so understanding transient power system conditions. We're training from scratch, and Emmanuel is one of our more recent hires. He graduated just over a year ago, and we've been getting him up to speed at a real steep learning curve. We have a couple of people that came from PSSE, but other than that, basically a start from the ground up and train to develop the in-house. You need to bring in people who have the skill set to do this kind of work, and it's doable. Like I said, we're very comfortable where we are. Debugging. We spend all our time fixing things with the case, working through the models coming from the vendors. Again, this is where we do a lot of our learning, so we're not complaining, but it does take a lot of the work. Okay, next. Now the hurdle to change is extremely fast. The documentation, the scripts, the criteria, we're trying to keep up with it. Every day there's something new changing. This floor here is basically, there's 8 of us here, which is a team that's working on this now. We've got special studies for all the projects. And that's challenging because you don't want to be having people continually working on documentation when you need them to be working on the studies and the testing. Models from the vendors have improved tremendously, but many iterations to get there. So getting that first model up and working, it comes in, we test it, we send it back and forth, back and forth, back and forth. That is actually the longest and most onerous part of this whole process. The EMT model testing, we've got scripts, we've got it into a really good state. It's just the time it takes to go back and forth to get it into a good working state. But when we say the models have improved, that means the control systems and the plants we are having coming onto our grid, starting this fall, they're under construction now, are in a much better state than they would have been if we had not done the EMT studies. We also have a better understanding as an entity about the support mechanisms for IBR. How do you integrate the highest levels of IBR? We're getting a pretty good feel for what we need in Nova Scotia. Control strategies, like how are you going to control voltage in this future world where you're going to have batteries, you're going to have the inverters on the in other entities. I'm sure you have solar, you have wind, we have HVDC links. This is not going to be a world where system operators are switching in and out static banks and moving tap changers. So we're going to a voltage control rather than power factor or, different types of control mechanisms. We're working through this. So we're going to be going with set point. Frequency hasn't changed a lot. That has stayed about the same. But I mean, what slope do you put on the droop for your battery versus your wind versus your legacy machine? So that's the kind of decisions that had to come out of our department as we're handing these projects over to operations. Next slide. I think I'm getting close to the end here. Okay, this was the NERC level 3 alert that just came out for folks that are in North America. And what they've determined to be essential to ensure reliable operation of the BPS is basically enhance the existing criteria and policies in our generator interconnection and planning activities, respectively, with additional technical details and IBR-specific performance criteria to address reactive power control, frequency response, ride-through behavior, post-disturbance performance. And this is exactly what we've been working through in these larger scale EMT studies. And to be able to perform those studies, we need those EMT models, control systems working well. So with the process here, it would take about 2 years starting now and being able to have the resourcing behind it to go from now to being able to do this. If you're starting from scratch, you're talking at close to 2 years to get the full way, but getting your criteria and your policies in place. If you go and take the information that's available to you, Nova Scotia Power, a lot of other entities have already created a lot of criteria and policies that align with this. So you could meet number 1 within 6 months. Just get into literature review. Feel free to copy anything we have. We're quite willing to share documentation, scripts, and process. We don't provide IT support when you find bugs, but we will share whatever we have. A lot of it would be in draft form, but number 1, you can get to fairly straightforward. Enhance modeling and study practice to ensure sufficient study work and control system performance and QT are performed. So they say request and review. We require the models and we review internally. Consultants are starting to ramp up for this, but there's still a bit of a lack in there for the kind of volume that is going to be coming. It's a really good opportunity here for consultants. Where applicable, entities should perform detailed review of currently operating IBRs under system to understand the extent of conditions of both real-world performance and accuracy of their models. This can be done in parallel. So number 1 is fairly straightforward. You can get in a few months. Number 2, it's going to take you probably to get to where you're flat, from nothing to flat out, you got probably close to 2 years. But you can get the models part up and running probably within 6 months to a year and be running it well. This third one about the existing fleet, our approach with this is we've gone back. When we got to PSCAD, we went back to like mod testing in North America. We test existing thermal plants. For IBR, it's a little bit more complicated. We have a variety of vendors, OEMs on our system, primarily wind, where we really don't have enough solar to be significant at this time. So when I say wind for a lot of North American entities, what you would be looking at would be solar. So let's just say we have XYZ models in a certain number of our wind turbines. And what we've done is we went to the OEM. We said, look, you've got these turbines were installed here 8, 10, 15 years ago. Can we get the parameters that were uploaded on site? So we had to get permission of the generator owner, and Nova Scotia Power owns some of these facilities as well. We're kind of vertically integrated, but you could require this of your GOs, that they give you the information that they have, or require them to go to their OEM and get the information. That would be what PSCAD model is the closest to the plant that's installed. What were the settings that were put in that plant when it was installed? So we did that. We actually, in our case, we got permission from the GOs. We got them to sign off, and we went to the OEM for one of our major turbine manufacturers that give us the settings you've got in these plants. And our models are performing very well. We've got a couple of really old ones that we don't have yet. When they become critical, the intent would be that we would test them and then tune a generic model to work. This one will be ongoing for some time. This one is 6 months. This one, this one's going to take some time. This one is up to 2 years. And then the GO, sorry, I was circling 4 when I meant to circle 3. The GOs create and implement process to help ensure models used for the evaluation of the design, submit it to the transmission planners and planning coordinators. we basically just said to the GOs, we need this. I can't speak for the GO because I'm not on the GO side. Next slide, please, Emmanuel. So the learnings from Nova Scotia, for anybody looking to start this, looking to come in compliance, and you have no significant EMT, I would say, unlike us, start with the model quality process for new facilities. It's an easy and relatively fast way to get to improvements in the facilities that are going to be interconnecting. Go there first in parallel. If you got the resources, start with the full system model, but start with the MQT process. It picks up a lot of the problems we're finding. In fact, the majority of the problems that we find and the non-compliance with these facilities is picked up in MQT. So the system impact study does address other aspects when the plant is going to be connected to the full system, but the MQT picks up a lot of the problems with fault ride through, reactive power management, looking at how you're going to, do settings to get the best performance for post-fault recovery. A lot of that's picked up in MQT. So start there. Then your base model, your big model, put a lot of time into working on the model that you're going to convert into EMT. I would have put it that we spent a lot of time on that, months and months and months. I recommend getting a really solid case with a good slider, a good single line diagram, so that when you take it into PSCAD, your team can look at it. It's a bit more intuitive to work from, and you're not trying to make massive change because you discover something was off. So start with a solid PSSE case or whatever your software is, get it in a good state, and then convert. Legacy plant tuning, you just use the best available models you have right now, and that will be ongoing over time, but you can use generic and get them up to a reasonable standard based on the knowledge of what type of turbines were used and what was installed in the field. Internal process training, documentation, again, this goes in parallel. For us, like I say, we got a lot of small training sessions internal. We had, like I say, our primary consultant, and one of them sitting right next to me here now from that company. Another one will be in. We have them sitting here in Nova Scotia, helping with the team. It's the fastest way to get people trained. That started this year, actually, with having them actually come here, because we have so many people, 3 or 4 people running different studies, and they have quick questions. It's easier to say, oh, grab somebody you're on the floor, than to try and get into emails back and forth, different time zones. So we found that that's valuable. Every month, a couple of months, have somebody come in for a week or two. Has worked really well to get to training. Documentation, I'll be retired long before we get cut up on the documentation. We're moving so fast right now, everything is at a date almost immediately. And for EMT system study, when we first started, this is like, oh my gee, we're trying to do this SIS, we're trying to do EMT, we just don't have time. All we got is one scenario done with the light load. Well, this is the most onerous one. Is what we know today more than what we knew yesterday? And yes, keep going. We published our first SISs for EMT study. We're very limited cases behind it, limited contingencies, limited tests, but it was better than nothing. That was the stepping stone that enabled us to get the experience to understand what we needed to start to see what was applicable for our system. Today, we can now run, like I said, hundreds of scenarios in the model quality to test, and the same thing with our large-scale studies and our SISs. We run a range of operating scenarios where we figure is going to give us the results needed, or what is the conditions that are likely to cause, oscillatory behavior or whatever. We run those scenarios. We've got hundreds of contingencies in the case. We pick whatever is needed. I would say we are in a very good state right now. So we're very open to anybody coming and asking questions. There'll be a limited amount that we can do to provide an IT type support, but we're very willing to share everything we have. I think that's the last main question. I'll see what we got here for a key question. Does Nova Scotia have serious compensation? No, we do not. SSCI, so we perform studies for projects, like if we've got subsynchronous interactions or subsynchronous control interactions, we do, based on the high penetration level of wind, all our EMT studies now are primarily high wind. Let me move the screen here where I can see it better. So if you want to come off mute and just talk to me a little bit about Andreas, if I'm not answering your question, feel free. But yeah, we do run studies specific to the case. I'm not sure. I'm sorry, I'm still getting my screens back open again. Okay. We have here, Andreas, again, have you considered using HPC to run multiple complex cases with single machine processing? So what we've got is we run Threadripper 64 core machines. Our model qualities we can run on our laptops. We have engineering laptops that are a little bit higher power, and we can run on that. For very complex cases, we can usually run them overnight or over the weekend, so we're not to where we need to do anything other than what we're doing right now. When Emmanuel was talking about the model quality, so he's got a Z book. It takes between 5 and 20 minutes to run a contingency, depending on time step and things like that. And he can run 8 at a time, and that's based on your license. So the license he used on his laptop can run 8 at a time. If I was running it on the Threadripper, I can run 64 contingencies, test scenarios at a time. So for us, we're good. We don't really need to go to HPC. Experience in using generic model and tuning the model to represent IBRs. It's not bad. Whether it matches field data, when we have those generic models in the big case, and there's only a certain percentage, like it's less than half, it doesn't put a significant impact on the results. I cannot say what would happen if we ran the full system with all generic models and then benchmarked against field data. So our field data has been based on our case, which does have some generic models because that was available. We did do large-scale models in about 2018. When we put the HVDC link in, that case had pretty well all generic models, and the results were reasonably comparable. But recommendation here is get the best model you can, because it's going to give the best results. When you get into looking at control interactions and high frequency damping, those type of issues, when we match against field data, we're matching against field data today, which is not a high IBR grid. What we do is we match the system we have today till it matches the case that we're running today. And then we say we're going to add this and this and this, and we have to count on that future imaginary system to tell us what we need to do. We can't really benchmark that really super high IBR grid because we're not there yet. So when we match against field data, we're matching our pre-IBR grid. It's getting an event where we can get good default has to occur, or the event has to occur, then we capture the data, then we match it against the PSCAD case. We don't have any of those with very high IBR. We're not there yet. Thank you. Emmanuel, this one is for you. What time step do you use for the MQT test? You had one demonstration there. It was running pretty fast. What was your time step in that one?
This one is 25 microseconds, but it ran pretty quickly because it's a generic model, so it doesn't really have any complex protection and control systems modeled. So that's why it was pretty quick. Yeah.
And we used a more generic case in there. A lot of what we have are under NDAs. Like we can't share a big PSCAD case, not even with consultants, unless they go and get a gazillion NDAs in place, which is why we tend to stick with one as well. So it's not like PSSE. You can go and get the MMWG cases if you're in in North America. So yeah, gets interesting. Question: how do you foresee the coming increase of grid forming inverters? So that was quite interesting. We have grid forming batteries going during construction. The first ones will be online this fall. We have updated our grid code to have different requirements for IBR depending on whether they're grid forming or grid following. To foresee the increase, well, what we found is increase the advanced capacity service for your network. Complex. I'm not really sure the nuance here. We have them. We have good models. We're putting them in. They're running well in both PSSE and PSCAD. They're just another type of device. More equipment. It's like, going from a VSC HVDC to an LCC. No problems whatsoever. Models, we spent again a fair amount of time in MQT with these back and forth. In fact, we got more revisions just recently because how we when we looked at the fast frequency response and the droop control for grid forming. But we require any batteries going onto our transmission system must be grid forming. We've had no problems. The models work well. They've been established also in Australia. No problems. It's easier to win. Let's put it that way. Similar to what you mentioned that some ISO have made their testing units. Yes, we are intending. We've got some consultants that are looking for it. We intend to release it. But that said, we are still developing. I'm sure you'll take it. There will be problems. We feel free to send us back anything and we may update our test kit, but we cannot provide IT support. Like Emmanuel ran a session for the Atlantic Canada Transmission Planning Committee there a little while back. So when he got up there, they bring up their laptops and everybody gets rated 1. Well, if the compilers got to be very specific, they run different compilers. I couldn't attend that meeting, so I'm not sure, but I know there was a lot of that kind of IT support thing. I'd say that's where you need to have a good working relationship with whoever your software vendor is. And again, like I said, we have them supporting us quite a lot this last couple of years to get us up to speed. So we are very willing to share the script, but it will be challenging to get your PSCAD set up and running and working well, or whatever your software of choice is. I mean, you could definitely take our script and look at it and see how you would do it in other software. I'm not promoting any particular software. It's just that is what we are working with right now. Published results of system. We have one that's going to be coming out this year. We put out the first version of the large-scale integration of wind 2 years ago. It's based primarily on PSSE plus literature research plus working with experts in the field to understand what we needed to do. We were going a bit slower into PSCAD than we were expecting due to the complexity of the models. So we now have the PSCAD results in particular looking at, the support you need for grid following and that type of support to get to the highest levels and trying to get that out. I was aiming for June. That didn't happen. End of the year is definitely a commitment. I just need a week or two to sit down, pull together the results that the team have in. We have it in draft. It will be coming out. To use ETRAN for PSSE, we used to, but for the studies and the size of the studies right now, what we do is we redispatch that PSSE to PSCAD. For larger entities, you may need to move to ETRAN. Like let's say in Canada, we have a system that load population-wise is very similar to Australia. So if we wanted to have an all Canada model of our electric system, we'd have to have it broken into sections and then you'd have to link them and run studies. If you could do that without ETRAN, I don't know. I mean, ETRAN is a good product. Like I say, we used it for quite a while before we've gotten to where we are right now. So we're not using it right now, but there may be applications where it becomes valuable again. Right now, we don't need it for our size of the system we're using, which is the Maritimes area, just 3 small provinces. If the intent is to get the most accurate information up front, which is not always possible, and if available, likely the technology and the product will change by that time. What's the process to handle those updates for the PSSE and PSCAD model? So say if it's a Nova Scotia Power project and we're actually the generator owner as well, we put it into our contracts with the OEMs that they will provide PSSE, PSCAD models for X number of years. once they're outside of that, because we have, we have some equipment, we have some plants on the grid where we don't have that, then we have to go pay to get it, which would be the expectation that the GOs will have to do that. It's hard to get the requirement. It depends if you have criteria, if you have requirements to do that for the GOs to give this to you. I don't know. That's something you're going to have to work out. Getting it up front, you're not getting connected in Nova Scotia anymore if you don't give it to us. Basically, we have a queue position to get an SIS. A milestone to get an SIS study is that you get models that pass our model quality test. That you just don't get in there. So if you don't get the information up front, it's a no-go. And then in future, put it into the contracts with them. But GOs, and I think NERC may support this soon for North American entities, they're going to have to do it, in which case you got to go pay to have it done. If you cannot get it from the OEM, then what would need to do is find somebody with PSCAD expertise that can take generic or the PSCAD, and I say PSCAD, this is for whatever software you're working with, you would have to take it and validate a generic model against test data. That's about the only thing I can think about it. Okay, go ahead.
Joey, can I add a little bit context to my question there?
Yep, go for it. Which one?
Yeah, my question really was that if the technology has changed in many different utilities or ISOs, you have the luxury to do the material modification study. Is that something, so you can perform a material modification where you would run some of the PSAC analysis, and then you would run some of the PSCAD wide area network, and then you resubmit that back to the ISOs. So in your case, I understand you're trying to get the most accurate information. So anything that you're getting in the first place is very unlikely that the exact same control system will be getting implemented 4 years down the road when this project is going to get built. So if it changes on the way, can we just resubmit it? Be like, okay, well, before we had a 4.5 megawatt turbine, and now we've got a 5 megawatt turbine, and from a different vendor, here's a new model. How would that impact your SIS studies as a whole? Or would you just not allow any changes whatsoever?
So changes like that, the GIP, Generator Interconnection Procedures for Nova Scotia, our province covers that. Basically, if it's a material study, and right now we would consider changing turbines, would need full assessment. So you'd need to come back to get a reassessment based on your turbines. If we get to commissioning and we go to commission and the results don't look the same, it's going to be up to the project to get models that match and work. And if it's a substantial change, then there's going to have to be an arrangement whereby the ISO, which would be us, has to rerun studies, which would delay projects. If they wait till the last minute and come in with, oh, we changed our turbine, sorry, we're going to say, so sad, too bad. It's going to be 6 months before we can even get you into process. Let's get set up. We run it, we test it, we go back and forth. It would definitely not be in the best interest of a project to have that kind of delay, because I can guarantee you in Nova Scotia, you will have a delay. We will not be able to turn it around that fast.
Yeah, I see it, but you understand, like, what I'm trying to say is that it will almost be very unlikely that any project that has come up with the models at the beginning, they be building it with exactly the same turbine and the same models by the time the GIAs are signed.
No,
right?
that's not our experience. Is very different than that. The models that they are bringing in now for the SIS that they're taking to their GIA, the turbines are ordered for most of them by the time we get to the end of the SIS, because that's why they really need that SIS so they can order their turbines. The HVDC link, we did tests on that 4 years before it went on service. We were involved all the way along, and it was very exact. That's not been our experience.
Very interesting.
So it might be different for different areas, but yeah, no, where our experience is that it's okay. I'm running over anybody. Let me see what got here. Go to computation time. I'm going to keep moving there. Which strategy have you used in order to increase computational efficiency? Well, the biggest one for that is, how big of machines have you got? What have you got? We're running Threadripper 64 core machines right now. like say, time step is the big one. And Manuel, you got any comments on that? But right now we're getting into, our focus has been more about getting it going with limited focus on increasing computational efficiency, because it doesn't take a huge amount of time right now. Okay, let's move on to the next one. Are the PSCAD modeling and testing requirements specific to transmission? So yes, we have in Nova Scotia for distributed resources, if it pushes back onto the transmission system, if the generation is greater than the load, it comes through to transmission planning. We are just starting to hit this now. The intent is going to be that we're going to set out the requirements. I believe it might be ISO New England. One of the entities I was talking to, they have a process whereby for IBR on distribution, they have this requirement for testing and a package, and there are consultants that do the test and deliver it. We're not as experienced in that. That is where we're going with this one. We also are starting to break out our distribution generation, and where it gets to be significant, it'll be modeled into PSCAD. Like right now in PSCAD, the distribution, the loads is just a load, and it's kind of a net load. We have started the process of breaking the load apart from the generation, because we're starting to get significant generation on distribution, and we're just getting into that now. Okay, Alex, how are you getting the OEMs to commit to model updates in the future? Is that an obligation you're placing on the GO and letting the GOs get a commitment from the OEM? It will be with the OEM. That's where it's coming to under NERC, and I believe that's one of the documents in that NERC alert was putting requirements on GOs. So it will end up under GO is my expectation. And as soon as we have any impact, or if we find that we can't get good modeling results, NERC will come down on that one, is my expectation. But right now, there's a limited amount we can do. In the longer term, but I'm expecting that to, like I say, that's going to be a GO problem. We can require the models of the GO. The GO is going to have to figure out how they're going to get the models to give to the system operator. If the system operator comes back and says, look, you've changed the software's changed, we can't model you correctly, we're going to go conservative, you're going to get curtailed more frequently, and it's going to be because of stability, you're not going to get paid, the model is going to be forthcoming. And that's kind of the scenario I can see it getting into. All right, we're running at 17:07. I don't see Alex. That good for you? You can jump off mute. Anybody got any last minute questions? But I'm going to wind down if that's what we have. Ooh, I talk fast. If everybody kept up with me, good job. Back on my computer. Oh, there I am. I'm back. Okay, anybody, any questions? I'm going to call it a day. All right. Thank you, folks.
Thank you. Bye-bye.